So we're going to do the following example. We have a curve C that's described via the vector valued function I have written up here. And our goal is to determine whether this curve lies on the given surface. So before we start this, we should really ask, well, what does it mean for a curve to lie on a surface? So the curve C will lie on the surface if every point on the curve also lies on the surface. So that really shouldn't be too alarming, right? But what does that mean? Or how do we actually work with that mathematically? So let's first note that if a point xyz lies on C, then there is a t-value for which x has to be equal to t, y has to be equal to 3t squared plus 2t, and z has to be equal to 4t plus 3. Remember, we call this vector valued function R a position function because it gives the x position, y position, and z position of a point on the curve. So this is what it means for a point to be on the curve. What does it mean for the point to be on the surface? Well, it means that if xyz is on the surface, then we also have an additional relationship between the x, y, and z coordinates. We know that 6x squared minus 2y plus z is equal to 3. So in order for this to lie on both, we know that x, y, and z can be expressed in terms of t, and that also x, y, and z are subject to the relationship given by the surface. OK, so all we have to do is substitute in for x, y, and z. So we know that our x is equal to t. We know that our y should be 3t squared plus 2t. And we know that our z is supposed to be 4t plus 3. And that's all supposed to be equal to 3. So since this is supposed to work for any point, we really have to show that this happens no matter what t is. So let's simplify this and see what happens. So we have a 6t squared minus 6t squared. Those go away. We have a minus 4t and a plus 4t. And when we do that, we actually notice that, that we have a true statement. So what does that mean? Well, that means that no matter what x, y, and z are, and no matter then what t is here, that this relationship holds. So we know that if a point actually lies on the curve, that that point also has to lie on the surface. So since this result is independent of t, hence the point on the curve C, the curve actually will lie on the surface. So that's a pretty cool example. It gives you this, it sort of reinforces this idea that when you're given a position function, you're always given x, y, and z. And when you have a surface, you have an additional relationship between them. To check if this curve lies on the surface, we just have to check for every t, and hence for every point on the curve, that the point also lies on the surface. So the algebraic consequence of how this works really isn't that difficult, but you should take a minute just to make sure that you understand the steps. And once you've taken that time, we can actually graph this, and we can determine visually, does this curve lie on the surface?